Hello, we are Memphis Community University, and today we are doing another Calculus Done Wrong lesson where we wrong calculus before calculus can wrong us. I have my eraser for mistakes, I have my marker. Let's try to learn some math. So today what we're going to do is we're going to talk about the fundamental theorem of calculus, the second half of the fundamental theorem of calculus. Still so fun that it's mental. So we have this. I think I spelled the theorem right. It would be embarrassing if I didn't. So for the second half of the fundamental theorem of calculus, what we're going to be looking at is we're going to be looking at derivatives of integrals. How exciting. So derivatives of integrals. So the previous two videos, what we did is we explored the first half of the fundamental theorem of calculus, which involved a formula with antiderivatives. Keep in mind that that half is the half that you're probably going to be using more often when you take these calculus assessments or when you're just having fun. But this half is still important, and what we'll see is that this is actually the easier half. This is the half that we prefer because we are just taking derivatives, and derivatives are lovely. So again, let's just be aware of that. Know how to do these questions, not too bad. So let's just get through a few theory things. Let's talk about the formula for the second half of the fundamental theorem of calculus, and then we're of course going to do some practice examples. So first off, what we need is we need a function defined as an integral because we want to take derivatives of that. So I'm going to write sort of the setup here. We have a x f of t dt. So I'm first going to talk about this integral, and then we'll talk about the derivative of this integral. So this integral is pretty complicated because there's a lot of variables, of course, but let's just go through it slowly and you'll see that it's not too bad. So just keep in mind that this is a function. The lower limit is going to be a generic number. That's why I denote it with an a. Could be 2, could be pi, could be 0, whatever number you would want there. The upper limit of this integral is actually a variable. It's x. It's very important, super important that you have this guy not match these variables right here, because what happens is, just like with any other function, what I want to do is I'm going to plug in things into this function, and how I'm going to plug it in is I'm only plugging in numbers into the x, I'm not plugging it into the t. So what I'm going to do is, let's say this bottom number is 0. If I wanted to find values of this integral, what I would do is I plug in 4, for example. And then what you would do is you would find the area from 0 to 4 between the function and the x-axis. So you do not want to plug in the 4 into all of this, because then you will evaluate the function and then it all changes and everything gets a little bit weird. So again, there's 3 things here. The bottom number really doesn't matter as we do these questions, as you'll see. The top thing is the important variable. That's the thing we're plugging in. The integrand with the t's, not as important. We're not going to plug into that. So that's that. And that's just the integral. So now we're ready to take the derivative. How exciting. So this is actually the fundamental theorem of calculus. You're taking the derivative of a function. The derivative of an integral, where the integral is kind of complicated, but we're still just taking the derivative of something. And what happens is we get something very nice on the other side. We get just f of x. So what is this saying? Remember that you might have encountered some inverse processes in previous math courses. Sorry, I lost my train of thought there. You might have done x squared and square root of x. You might have covered e to the x and ln x, sine x, inverse sine of x. So basically what the fundamental theorem of calculus part 2, why it's so beautiful and why it's so useful is that it says that if you're taking the derivative of an integral, basically they're inverse processes, so they sort of cancel each other out. So when you have this guy right here, all you're going to be left with is this function. So if I take an integral and I immediately take the derivative, I just end up with the same thing. How nice. So what we're going to see is that some of these questions are just like the easiest questions in the world, basically. So that's just the fundamental theorem of calculus. We're going to be practicing with this quite a bit. Keep in mind, though, that the fundamental theorem of calculus is a derivative question. So anytime you're taking derivatives, what you always want to be aware of, is that you might be needing to employ the chain rule, the most important rule, of course, because sometimes you're going to have inside functions. So I'm just going to write this, and we're going to talk about this later. But you should always be aware that you might need to use the chain rule. And just keep in mind that there looks like there's 2 inside functions in this bigger function, But the actual inside function that we care about is only the upper limit. So chain rule, the thing you plug in. So again, what we're going to chain rule is we're going to chain rule this upper limit with the x's. We're not going to chain rule the t's because when we do this, we're going to plug it into this function here. We're going to evaluate it right here, and then that's the inside function, and then we plug it in. This sort of doesn't make sense because I'm not explaining it incredibly, but you'll see that when we do these examples, if you understand the method, it's not going to be too bad. It's not going to prove the fundamental theorem of calculus. That would be doing calculus the right way. Let's just go straight to examples. So let me erase this guy. Let me see how fast I can erase. Sort of a workout, but I think I can do it. So we have this. Let's tuck the fundamental theorem of calculus in the corner here for ease of access. So again, it says the derivative of an integral, no matter what the bottom number is. A little bit got the top there, but that's going to be okay. It's just the function. So this is the thing we're going to be using. Keep in mind that in this setup, the x has to be on the top. That will come in the second question. But again, the a doesn't matter whatever number you have. So let's do our first question. So we have d dx of, again, you can choose any number you want. I'm going to choose the number 7. Crazy. We have x here, and then we're going to have a function. Let's just make it simple. Let's choose secant of t. So this is my question. So what we're going to do is we're just going to apply this formula, which is the best formula in the world, the fundamental theorem of calculus, and then we are going to employ this formula for this question right here. Notice that the setup is really similar. This is just a specific example of this guy right here. 7 is a, x is the same, the function in the middle is secant, and then we have a derivative. So alarm bells are ringing. We are taking a derivative of an integral, fundamental theorem of calculus. So when you take this derivative, again, all you do is you just plug in the x and just see how easy this is. See how lovely this is. Let's appreciate it. All we do is we take the x, replace this guy, and that's the answer. Wait. Yeah. Wait, that's all you do. Okay, so again, it's one of the easiest questions. The 7 doesn't matter at all. The integral and the derivative basically cancel each other out. Of course, the integral and the dt are paired together, so when you cancel it out, everything goes away. All you do is replace the x, and that's it. So again, pretty lovely process, pretty easy process. Everything is canceled out, so if you square something and square root it, we'll just get the same thing back, and that's what the integral does. So let's try a little bit of a harder question. As you can imagine, it's not always this easy. So we're going to have the same format, d dx, but instead let's have a number on the top this time, and then on the bottom here I'm going to have x again, and then for the function really doesn't matter because it can just be any function, because all we're doing is plugging in x into that function. But let's try to make it a little bit more complicated. Let's try to have it as ln, squeaky, of t plus 4t dt. Probably going to run out of room, but sometimes that happens. Sometimes you got to go with the flow. So let's take this question right here. So for this question, notice the only difference besides the function, you're still taking a derivative of an integral, is that the x is on the bottom, which is kind of what we don't want. We want the x to be on the top because the fundamental theorem of calculus says that you need the x on the top in order to employ it. So what we need to do is we just need to take this guy right here and somehow make it over here. But if you watch our previous video on integrals of properties of integrals, what happens is if you want to flip an integral, if you want to flip this bad boy, what you need to do is you just need to negate the integral. So if we want to perform a flipperoo, all we're going to do is we're just going to have the same guy and we're just going to write negative instead. X on the top now. This guy, none of this changes. All we're doing is performing the simple step. Hopefully you can see this. Hopefully I'm not in the way here. As I'm rushing through this to try to get out of the way and I'm miswriting it, but that's how life goes. So again, all I did is just one little step is I flipped the integral because I want the x on the top. And in order to do that, you negate the integral. Keep in mind that we're still taking the derivative, so I'm going to still take the derivative. And now we are doing the level of the last question. So we have a negative here, because that came from the flip. And then what we're going to do is we're just going to plug in this x into these variables. So now we are in the fundamental theorem of calculus format. The x is on the top, the constant is on the bottom. We are good to go. Some of my students get confused at first, or confused a little bit, because there's two variables to plug in. They're like, what am I going to do? What am I going to do? But of course, all you're going to do is just you're going to place all the t's with x's. It's not that much harder. So it's going to be negative ln of x plus 4x. And that's it. Again, the derivative gets rid of the integral, gets rid of the dt. Plugging in this little guy into your t, plugging into your t, this negative is from this flip that we performed at the beginning of the question. So just one more step, flipping that integral. And that's basically it. So these are the easiest questions, of course. Let's try to spice it up a little bit with the chain rule, as I alluded to in the intro. So let's do that. So keep in mind that these chain rule questions that I'm about to do, that's really more of the level of the AP exam. You should expect maybe one of the following sort of difficulty questions in the multiple choice section around number 17 or so on the non-calculated multiple choice. So here we have a function, or a derivative actually. Bottom number really doesn't matter. We're going to choose 3 this time. Top number. So instead of just having x in the top here, we're going to spice it up a little bit, and we're going to write x squared instead. And then we're going to have a generic function here. Let's have it as 3t plus 2. So again, this is a chain rule question because notice that your inside function, and remember that the inside function is this guy right here, so sometimes I like to circle it for fun. It's this guy and not this guy. So again, what we're doing is we're plugging in this guy, plugging in the x squared into your t, so every single time we have a t, we're going to replace it with x squared. So chain rule, the plug-in. And not the thing we're plugging into. This is the plug-in, this is the thing we're plugging into. So we're going to take this guy with our dainty little hands, plug it in, and then we'll use the chain rule at the end. So again, the same thing is we're just going to have 3x squared. So notice instead of this t, we were like this, we just wrote it like that, and that's all we did. We still have this plus 2, don't really care about that. So this is where the chain rule comes in. So at the very end of this guy, notice I'm not going to multiply by 3, which is the derivative of this. I'm going to multiply by x squared, or x squared's derivative, which is 2x, because of the power rule. I'm multiplying by the derivative of the thing I plug in, not the thing I plug into. Please, 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 just remember that you're always multiplying by the derivative of the thing you plug in. So, for example, in our previous questions, when we were plugging in x, we were technically multiplying by 1. So in this case, we're going to multiply by 2x. So yeah, just remember that chain rule. The chain rule is the most important thing of all time besides the fundamental theorem of calculus. So this is the answer, actually. Let me just point out one more thing. So some of my students, because they learned some things from me, they will remember this 2x, but they're working too fast. They're too excited about calculus, and they'll forget to multiply this 2x by everything. So just be very careful with parentheses as usual. Wrap this entire original thing with parentheses, and then on the outside of it, what you're going to do is again multiply by the derivative of this guy right here. So I'm going to write an example on the board here. Let's write 5. Let's write, my 5 is really bad and it doesn't matter. 5, let's write ln of x. Why not? And then in this function here, we'll write 1 over, no, let's not do that. Let's not do that. Obviously, I'm not very prepared. What should we do? What should we do? It doesn't really matter. Let's do square root of t, 2t plus t. So why don't you try to pause the video, work for 3 or 4 seconds, maybe more than that, maybe 20 to 30 seconds, maybe a minute, who knows? Just try this question, and then after a few seconds, I'm going to do the question, assuming that you did pause the video. So let's wait for 3 seconds. 3, 2, 1, let's go. So again, as long as you remember sort of my plea, remember the chain rule, we should be good to go. So we have this top function. We are taking a derivative of an integral. That is fundamental theorem of calculus. We're going to take ln of x, put it in all these t's, just take it and shove it in there. So what we're going to get is we're going to get 2 square root of ln of x plus ln of x, because notice that I have 2 t's here, and I replace both of these t's with ln x. I plug in the top thing into this guy right here. Of course, we are not done. If you were taking a AP exam, this would be a multiple choice question because they're trying to trick you. They're trying to see if you remember stuff, and I don't usually remember stuff. So what I need to be careful of is I need to multiply by the derivative of the inside, the thing I'm plugging into. Sorry, not the thing I'm plugging into, the thing I'm plugging in, because that's the chain rule. So at the very end here, I'm going to multiply by 1 over x. Some of my students would multiply by, for example, the derivative of all this, which is more complicated. It's 2 times 1/2 t to the negative 1/2 plus 1, but notice that that's not what you do. Again, all you do is multiply by the derivative of the inside. So hopefully you got that correct. If you didn't, don't feel bad. We're just learning something new. But just keep in mind that it's not the hardest process in the world. Just take your top thing, plug it into the function, and then multiply by the derivative of the thing you plugged in. So that's the fundamental theorem of calculus. And you should expect a question on the multiple choice or perhaps any college calculus exam in Calc 1 of this level. But we're not done, unfortunately. Sometimes there are, of course, harder questions. So let's see this sort of process in action and sort of harder questions. So I'm going to erase the fundamental theorem of calculus because I think we know it by now. Derivative of integrals are just the function. And let's do this question right here. So we have limit as x goes to 2. We have x squared minus 4 on the bottom. And then we have an integral. Let's have t cubed. Hopefully that's not too crazy. Let's have 6 and 3 t, not t. Gotta be very careful when you're constructing these questions and also when you're doing these questions about the variables you choose. So again, I don't want these to match, so that's why I had to change it. Let's multiply this by 1 dt. So this is a pretty treacherous question, if that's the right adjective. It's a multiple step question, and a lot of times my students complain about multiple step questions. But if you just take one step at a time, you'll see that the question isn't actually too terrible. So let's see what's going on. Imagine I don't know that we're in this lesson. I just look at the page, I see a beautiful problem, and I'm going to do it. So I see the limit. This is inherently a limit question. It's a weird thing in the numerator, sort of ignoring it for now. So I have a limit. What do you do for limits? Well, the first thing you want to do when you have a limit is just plug in whatever the x is going to into your thing and just see what you get. If you get a certain thing, which we'll actually get in this one, of course, we do a certain process. So let's plug in 2 and see what we get. To build up my confidence, I like to plug it into the easier guy. Looks like the denominator is easier, so I'm plugging in 2 here. 2 squared minus 4, 4 minus 4, I believe that is 0. It's now time to see if I'm ready for the show. I'm going to plug in 2 into this. So again, just keep in mind that the x is on the top. There's t's in the integram. Only plugging in x, this 2 into the x's, because it says x to 2 and not t to 2. So when you're plugging 2 here, I again plug it only into the top. I get 3 times 2, which I believe is 6. So you have 6 on the top of the integral and 6 on the bottom of the integral. And here comes another integral property that we talked about. Whenever you have the same number and the same number on an integral, that integral is going to be 0, no matter what the integrand is, because you're having 0 area under that function. So I don't even need to look at the integrand. I'm just going to see that it's 0. So we do get 0 over 0. And when you get 0 over 0, when you're taking calculus, both the AB and the BC level, there's a process. It is time, friends. It is time to L'Hopital's. And what I mean by L'Hopital's is, of course, L'Hopital's rule. So we're going to apply L'Hopital's rule. I would probably write it a little bit more precisely if I were doing this on a free response, but here we're just having fun. So I'm applying L'Hopital's rule. So remember what L'Hopital's rule says is you take the derivative of the top and the derivative of the bottom. So I'm going to take the derivative of the bottom first. Again, I like to do easier things just to build my confidence a little bit. So the derivative of the bottom using power rule is just 2x. So now I look at the top and it looks really nasty and I don't want to do it and I'm scared. But it's going to be okay. It's going to be okay. Because notice what is the top. The top is an integral. And what do? We are taking a derivative of an integral in the context of a limit, because that's the L'Hopital process. Take the derivative of the top and derivative of the bottom. But when we're taking the derivative of the top, it happens to be an integral. That's the fundamental theorem of calculus. So we're going to be using the fundamental theorem of calculus inside other questions whenever we need to take a derivative of an integral, and this is the time of this question. So we're going to take this derivative of this integral, applying the fundamental theorem of calculus that we just used earlier. So what we're going to do, just like our previous questions, is we're going to take this 3x, plug it into the t, right here, 3x. Again, you want to be very, very careful with parentheses. What is replacing t? Not just x, it's 3x. So notice that t was originally being cubed, so 3x should also be originally cubed. This minus 1 is just on the outside, so we're going to write minus 1. And then what's the one thing you have to remember in these questions? The chain rule. So when you take this chain rule, we're going to multiply by the derivative of the thing we plugged in, not the thing we plugged into. So notice I'm not going to write 3 times something squared. That'd be the derivative of this guy. I'm just going to write the simple number 3. So it's going to be times 3. And notice that if I wrote it like this, I would be in a little bit of trouble because I might multiply everything wrong. I'm going to wrap this guy around with brackets or parentheses just to be careful. Again, you plug in 3x, finish your line, and then multiply by the derivative of the top thing. Whew. So notice though that once we hit this step, we apply fundamental theorem of calculus because we had to take the derivative of the numerator, which happened to be an integral, and that's when you use the fundamental theorem of calculus. And now we arrived at this step. And when we arrived at this step, notice it's not too bad. Sort of out of breath, I don't know why, but you plug in, there's the 2 for this x, see what you get. Hopefully you won't get 0 over 0 again, and you're just going to get a number, which I believe will be in this case. So let's try to wrap this up. When you plug in the 2, again, you're going to multiply 2 times 3. Unfortunately, I'm not ready for this because you're going to get 6 cubed. So it's going to be 6 cubed minus 1. All of that times 3 over 2 times 2. So again, all I'm doing is replugging the 2, but I was careful. The 3 is also being cubed, so that's why it's 6 cubed, 2 times 3. Do I know 6 cubed? I don't know 6 cubed, or at least I don't want to guess it. So no shame in doing math on the side. Probably shouldn't have made numbers this big, but whatever. 6 times 3, that's 36, of course. 6 times 3, 18, 216. I think I maybe knew that, maybe didn't. So it's going to be 215 times 3. 215, this is the least important part of this video, but it's 215 times 3, that'd be 645 maybe over 4. Look like we got my favorite number in the world, 645 over 4. Again, the number doesn't really matter. It's really all about the process. So I'm going to repeat the process, and hopefully I'm just going to assume that I multiplied these things right. And that's like a 50% chance that happened. So again, we have a limit. Anytime you have a limit, you should just plug in the number. If you get 0 over 0, look that tall. What that means is that you take the derivative of the top, the derivative of the bottom, no matter what you need to do to take those derivatives. So the derivative of the bottom was just a very simple derivative, but the derivative of the top required the fundamental theorem of calculus, which we just learned. All we did is we plugged in the top thing into our t's, because this is the fundamental theorem of calculus. This is how you take derivatives of integrals. They cancel out. So we're taking a derivative of this integral. We plug in the 3x. Keep in mind we were very careful with the 3x being in parentheses, and then finally the chain rule. And then after that, once we did that step, no more integral because the fundamental theorem of calculus got rid of that. So all we did was we plugged in 2, got our number, boom, 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 boom. So let's do one more question similar to this where it's not technically a fundamental theorem of calculus question, but I will use fundamental theorem of calculus because in this question, we'll eventually take a derivative of an integral. Sorry to spoil the fun. So let me erase this real quick. Not gonna erase this fast because I need to catch my breath. I don't really care about the dots. Hopefully you don't care about the dots. I'll try to get a few of them. Let's get going. So last question. So let's say we have this function here. I'm gonna say, let's say x squared minus 6x minus 7 We're not going to have that. We're going to have t's instead because we're going to take this integral. We're going to put x on the top. I can't put an x here, so hopefully that makes sense. The bottom number really doesn't matter. We'll put it in as -1. Always nice to have a dt. So this is my function. This is my given. Notice that it is an integral, so if I have to take its derivative, I have to do a fundamental theorem of calculus. We're going to do that. But the question is, where is f decreasing? So just like that limit question, it is nice to maybe foresee the future and foresee, oh, fundamental theorem of calculus. But I like to take everything step by step. If things come about naturally, I just use those things when they come up. So I don't even look at the function for now. All I'm looking at is the question, where is f decreasing? So the rule for f is decreasing is that f prime is negative. So I think about that. How do you tell if f prime is negative? Well, you take the derivative, draw its sign chart, and then see where it's negative. So I'm taking my function here, I'm looking at it, and I'm closing my eyes, and then I finally look at it, and I'm like, oh my god, this is awful. But it's going to be okay, actually, because this derivative is easier because we're doing fundamental theorem of calculus. It looks intimidating because it's an integral, but it's going to be easy. The fundamental theorem of calculus is easy to apply. So I have f prime of x. I'm taking the derivative of this integral. All I do is take this x and just nicely put it into these t's. So it's going to be x squared minus 6x minus 7. The t's go away. The integral goes away, the dt goes away because I'm taking the derivative of the integral. That's what my friend, the fundamental theorem of calculus, says. Nice to listen to your friends, of course. Just keep in mind, though, that we took a derivative. From this step to this step was a derivative. Sometimes my students think that this process is so easy that they don't think that they've already taken a derivative, so they'll take another derivative, but that actually is the second derivative of f. So for example, if you're looking at this, the second derivative of f double prime would be 2x minus 6 using the power rule. But just keep in mind that it looks like we didn't do very much, but we actually did take a derivative by the fundamental theorem of calculus. And just like with that limit question, this is where the fundamental theorem of calculus came about, because we had to take a derivative of an integral. So now that we're done with it, we're just going to employ normal strategies. So f is decreasing when f prime is negative, going to factor everything, because that's how you do these sort of shapes and curves questions. You want to draw a sign chart. So it's going to be x minus 7, I believe, x plus 1. This seems right because it's minus 7x plus 1x. So now we're drawing the sign chart. Second most famous sign chart maybe. Just a nice little parabola here. Regular size parabola, like eating the sky, I guess. -1 to 7. Positive, negative, positive. And anytime I have shapes and curves question, we might as well answer it as precisely as possible. I always like to put 3 things: the question itself, the justification, and the answer from the sign chart. The AP exam explicitly says that the sign chart gives you 0 points. It's the sentence that goes with the sign chart that gives you the points. And we want the points, probably. So we have f is decreasing. The rule is f prime is negative. And then what's the interval? -1 to 7. So I'm going to recap this question because I like to hear myself talk. But I was given this function. I wanted to see where f is decreasing. I know that f is decreasing requires me to take the derivative and see where it's positive or negative. So I looked at the function and I was like, oh, this function is an integral. I know how to take derivatives of integrals. That's the fundamental theorem of calculus. So I took this derivative, and how to take the derivative of integrals is that the integral and the dt go away. So you're just left with the function. And then when I was left with the derivative, just with that L'Hopital question, it just becomes normal stuff. Just factor this sign chart, draw the sign chart. It was a parabola. We saw where it was negative. We are good to go. So hopefully you can see that these fundamental theorem of calculus part 2 questions, taking the derivative of integrals, let's just recap, isn't too bad. They're inverse processes, so they really cancel each other out. They do occur in other questions, but just anytime you have an integral and you want to take its derivative, fundamental theorem of calculus. So it's derivative of an integral, f of t dt, a to x, 7x. What was the big point? what's the one thing, the most likely mistake that people have, the thing that they're going to try to trick you with the other multiple choice answers? Well, it's the chain rule. So remember the chain rule. This is supposed to be a star. And then remember that what we're chaining is the thing we're plugging in, the thing in the upper limit. So the thing, plug in, upper limit. So this has been a little bit too long of a video for an easier topic in my mind. This is probably the easiest video in this playlist as we're doing integral topics. Again, I think the fundamental theorem of calculus part 1 is a lot harder. The next video, as a preview, is we're going to talk about averages. That's probably harder as well, average and average rate. But still nice to know. I always want to see a fundamental theorem of calculus question when I'm taking a math exam, whether that be forced or for fun, because I know how to do these questions, because again, they're still derivatives. Derivative of integrals cancel out. If you want more practice of this, of course, we had a girls teach calculus video where one of my former students practices several more of these examples. So she'll practice very simple ones, but she'll practice things that you need to flip. She'll practice some that require the chain rule, as we did before, and also questions like limits with L'Hopital's rule and shapes of curves question, where when you're taking derivatives of integrals, you do need to use that fundamental theorem of calculus. So be sure to check out that video. She probably explains things better than I do. But thanks again for watching. As normal, like and subscribe if this was useful, and hopefully I will see you next time as we talk about averages. Thanks again.